China's path to satellite broadband has been very difficult. While not an early leader in the commercial satellite space, it is quickly catching up, trying to become a dominant force in satellite broadband, overtaking the Europeans. For decades, China's space sector was behind the Americans, Russians, and even the Europeans. But in recent years, they have eclipsed all the previous dominant players except the US. China's LEO ambitions are not their first space grand projects. China now operates the Baidu navigation satellite system, a fully functional global navigation system that serves as a direct alternative to US GPS. The country has independently constructed and operates the Tiangong space station, which has been continuously crewed and hosts a wide range of scientific experiments demonstrating advanced capabilities in long-duration human space flight, orbital operations, and space-based research. But while the country now has a good foundation in rocket delivery, satellite communications, and navigation, building a global broadband mega constellation is a bit more complex and expensive than these past projects. After the US started encouraging its companies to enter the space economy, many other nations followed suit. In 2014, the Chinese government opened their space sector to private investment, unleashing a wave of startups. This policy, combined with the impetus of watching Western programs like Starlink advance, triggered a national focus on space as a critical domain. Satellite internet was officially added to China's list of new infrastructure priorities, signaling full state backing. But unlike for its EV industry, where each Chinese region fielded their own local champions, multiple programs were consolidated under the state-owned China Satellite Network Group to create two main projects: the state-led Guowang National Network Constellation and Shanghai's Qianfan Constellation. Guowang's main goal is to create a secure state-controlled communication system independent of foreign providers. It plans a massive multi-orbit constellation of over 13,000 satellites. The Qianfan constellation has plans for up to 15,000 satellites targeting international markets. This arrangement actually mirrors most of China's other industries, where state-owned entities compete with private enterprises, allowing the state to retain control over some core strategic assets but allowing private competition to boost efficiency. This is compared to the US, where private companies are taking the lead in building constellations, but also involve collaboration with government agencies like the Department of Defense and NASA. China's Guowang satellite constellation represents Beijing's most ambitious space infrastructure project, designed mainly to achieve technological sovereignty. Announced around year 2020, the project consolidated earlier Chinese initiatives, the Huangguan and Hongjian constellations. Guowang, which translates as National Network or State Grid, is being built by the China Satellite Network Group company and is managed by a mix of state-owned entities, including the China Aerospace Science and Technology Corporation, its subsidiary, the Chinese Academy of Space Technology, and private companies like Galaxy Space. Unlike purely commercial ventures, Guowang is widely believed to have integrated civilian and military applications, a factor enhanced by a notable lack of public technical details about its satellites. Analysis of its architecture reveals it's a two-tiered system, the GWA-59 and GWA-2 constellations, with about 6,000 GWA-59 satellites planned for orbits around 500 to 600 kilometers and 7,000 GWA-2 satellites for the higher orbit at approximately 1,145 kilometers. This two-layer approach likely allows it to support a broad range of applications beyond internet service, including remote sensing, navigation, and secure government communications. They also plan to launch D2D direct mobile-to-satellite communications in the future. A sovereign constellation provides the People's Liberation Army with secure, resilient, and jam-resistant command and control links that are entirely independent of foreign infrastructure. This is critical for coordinating deployed forces, ships, and aircraft, as well as for guided advanced weapon systems like drone swarms and hypersonic missiles. Reliance on a foreign system like Starlink is viewed as an unacceptable risk because access could be denied or monitored during a conflict. This need for absolute control extends to securing critical national infrastructure. Sovereign satellites will provide secure data pipelines for sensitive operational networks that, if compromised, could cripple the nation. Examples include real-time monitoring and control of nuclear power facilities, the control systems that manage the national power grid and urban heating stations, the ultra-low latency data feed for financial markets, trading and settlement, and the redundant backhaul for national 5G, 6G telecoms backbones. Using foreign satellites for this traffic created data sovereignty risk, exposing vital systems to potential interception or sabotage during conflicts. For law enforcement and emergency services, a sovereign network guarantees uninterrupted encrypted communications. This will enable secure field operations for police and border patrol, reliable coordination for disaster response teams when terrestrial networks are down, and the transmission of secure video from body cams and surveillance UAVs. It ensures public safety communications remain under sovereign control during crisis. GoOne aligns with China's broader space infrastructure goals outlined in its 14th five-year plan. Its lower tier of about 6,000 satellites at 500 to 600 kilometers will prioritize ultra-low latency, enabling real-time applications like drone operations and missile guidance. The upper layer of about 6,900 satellites at 1,145 km altitude will sacrifice speed for expansive coverage over oceans and remote areas. This bifurcated approach will allow China to concentrate high-performance assets over strategic regions like the South China Sea while maintaining global surveillance capabilities. In contrast, Starlink's single-shell model at 550 km emphasizes uniformity. With over 10,000 operational satellites and plans for about 42,000, its homogeneous grid delivers less than 40 milliseconds latency worldwide. SpaceX leverages unparalleled launch cadence of 60-plus satellites per Falcon 9 mission to achieve constellation density impossible for competitors. Starlink's V2 mini satellites broadcast at Ka bands at between 26 to 40 GHz for uplink and Ku bands at between 12 to 18 GHz for downlink and cutting-edge EV bands at 60 to 90 GHz for satellite-to-satellite backhaul, with 200 gigabits per second optical laser interlinks to help deliver 220 megabytes per second download speeds. A single Starlink satellite can serve approximately 16 beams, with each beam capable of providing about 6 gigabits per second of download throughput. This commercial focus enables Starlink's direct-to-consumer model, serving over 10 million users with plug-and-play terminals. While the exact details of GoOne are closely held, industry analysis and filings indicate it utilizes Ka bands at between 26 to 40 GHz for user links and QV bands at 40 to 75 GHz for high-capacity feeder links and inter-satellite links. This use of high-frequency spectrum, particularly the experimental QV band, is aimed at achieving high throughput to compete with other mega constellations. The system's design target is to provide user speeds exceeding 100 megabits per second with latencies below 50 milliseconds, matching modern low Earth orbit broadband standards. When it comes to radiation levels, while LEO is partially protected by Earth's magnetosphere, it's still exposed to penetrating proton flux and cosmic rays. This is especially severe in the South Atlantic anomaly, a vast region over South America and the South Atlantic Ocean where Earth's magnetic field is weakest, allowing radiation belts to dip closer to the surface and dramatically increasing flux levels. Secondly, the radiation threat composition shifts with altitude. Orbits above approximately 1,000 kilometers encounter intensified belts of trapped electrons, which contribute to cumulative total ionizing dose damage in electronics over time. To endure this environment, LEO satellites employ a multi-layered protection strategy. At the component level, they use radiation-hardened electronic chips often made of semiconductor technologies like silicon on insulator or gallium nitride. At the system level, critical subsystems are shielded with high-density materials like tantalum or advanced multi-layered composites to attenuate radiation and mitigate long-term damage to sensitive components. This combination of hardened electronics and physical shielding help ensure multi-year operational lifespan of modern LEO constellations. Starlink's 550-kilometer orbit suffers intense atmospheric drag during solar storms, making them susceptible to single-event upsets from proton flux, reducing design life to about 5 years. About 40 satellites were lost in 2022 alone due to unplanned re-entries. Their current satellites weigh about 800 kilograms and are fitted with argon-ion thrusters, which help keep them in orbit. The Go-1 constellation, designed with satellites in both lower and higher low Earth orbits, faces a complex orbital environment that directly impacts its design and operational logistics. While satellites in its lower tier, at around 500 to 600 kilometers, experience significant atmospheric drag and are within a region of notable proton flux radiation, the satellites in its proposed higher tier, at around 1,145 kilometers, encounter a different set of challenges. At this higher altitude, atmospheric density is drastically reduced, leading to over 80% less atmospheric drag, but flux of higher energy trapped ions increases, contributing to greater cumulative radiation doses. This strategic multi-layered architecture creates a key operational trade-off. The significantly reduced drag for the higher altitude cluster will extend satellite lifespans to an estimated 7 years or more, compared to the roughly 5-year design life for typical lower clusters and comparable constellations like Starlink's Constellation. However, maintaining a continuous full-scale constellation still requires a massive and sustained rocket launch campaign. For a 10,000 satellite constellation with a 7-year average lifespan, approximately 1,430 satellites will need replacement annually to maintain the fleet. Assuming each heavy-lift rocket could deploy 50 to 70 satellites per launch, this would necessitate a relentless pace of 20 to 30 dedicated launches every year to maintain the upper cluster, and almost twice that to maintain the lower cluster. But without reusable rockets, China could only launch about 70 rockets in 2024 and 93 in 2025. To sustain a satellite constellation exceeding 20,000 satellites, especially with multi-year operational lifespans, the required launch cadence becomes a dominant engineering and logistical challenge. For even bigger constellations of more than 20,000, you will have to launch more than 100 rockets per year or utilize a bigger super heavy class of rockets. Between the Go-1 and Qianfan constellations, China plans to launch more than 20,000 satellites, but maintaining 20,000 satellites with a conservative 7-year average lifespan requires launching nearly 3,000 replacement satellites annually. The Chinese started testing reusable rockets in late 2025 and had yet to succeed, so the first group of satellites launched will have to use expensive single-use rockets. Launch efforts currently rely on China's Long March rocket family, particularly the Long March 6 and 8, which are non-reusable rockets. But agreements have been signed with Landspace to utilize its Zhuque 3 reusable rockets as soon as they become ready. Other private launch companies like X-Space with its methane-fueled Hyperbola 2 rocket aims to bolster launch cadence to 50 to 100 missions annually post-2025. Initial Go-1 deployment will focus on mid-inclination orbits to prioritize connectivity over densely populated areas, with later phases expanding to polar orbits for comprehensive coverage. Deploying at rapid pace, Go-1 has surpassed 100 operational satellites in orbit as of late 2025, but it still faces immense challenges in launching the thousands more needed to meet its ambitious goals. Go-1 will not outsell Starlink in America or Europe. Its competitive advantage lies in dominating its local market and in the global south markets, where price is the main determining factor of success. By 2030, Go-1 aims to capture a slice of Africa's satellite broadband market and 70% of China's rural connectivity, serving 50 million subscribers despite Western exclusion. China's huge population provides Go-1 with a captive launch market. Despite 5G expansion, 107 million rural Chinese households still lack broadband access, particularly in western mountainous provinces like Tibet, where fiber deployment costs are exceedingly expensive, making satellites the only viable solution. China's data security law mandates that data pertaining to national security and public interest must be stored domestically and be accessible to the state. A sovereign constellation ensures that routing for highly sensitive information such as citizens' health records or encrypted political and diplomatic correspondence between government agencies never passes through foreign-owned orbital infrastructure, shielding it from foreign surveillance or legal interception. This constellation will be essential for controlling the public space and enabling next-generation technologies. It will allow for an extension of China's cyber governance model, often called the Great Firewall. This will allow the communist government to retain control over the narrative in its local public square and prevent geopolitical rivals from controlling the narrative locally. China also sees satellite constellations as a foundational piece of 21st century infrastructure. Go1 will provide the secure, high bandwidth and low latency data pipelines required to serve artificial intelligence models and to reliably operate autonomous systems like self-driving cars, electric vertical takeoff and landing aircraft, and robots, which are all central to China's future technological ambition.